Hello, students. So, in chapter 16, we're going to start talking about the kinematics of rigid bodies. So, let me define quickly what a rigid body, what we understand for a rigid body. So, we have a point, right? So, we study the kinematic and all the physics of a point and the forces. So, a rigid body has some extension. And so it has many points, and the key feature is that the distance between these two pairs of points within the rigid body never changes. So it has a size, it has shape, and it can have a very complex motion. And the purpose of this chapter is to study the kinematics of that complex motion. So we're going to concentrate on just planar motion, motion in a plane. The we can extend this to 3D very easily. It's a little more complex, but once you understand the fundamentals of planar motion, the fundamentals of 3D motion is not going to be very complicated. So we're going to understand the kinematics of a rigid body motion. We're going to break it into three different possibilities. We're going to have translation, pure rotation, and a combination of both, translation and rotation. So the translation, you can see here that what happens is if you have these lines here between 2 points, those lines never change orientation. So as the body moves, these lines always have the same orientation, right? So this one is vertical and it's always vertical. Here, this one is vertical and it's always vertical. So this is the key defining feature of translation. So you can have rectilinear translation, or you can have curvilinear translation. And when you have translation, you just use the techniques that we've used in previous chapters to study this. Then you can have pure rotation. In this case, there is a point or a set of points in the body that never move. So all the points in the axis here, they are not moving, and everything is rotating around that. So that's the key feature of translation. And if we combine both translation and rotation, we get the general plane motion, which is the most complicated motion that we're going to study. So translation, let's just look quickly at translation. They could be both rectilinear and curvilinear. For rectilinear translation, we use the techniques from chapter 12. And for curvilinear translation, we are going to have, well, tangential acceleration and a normal acceleration. And we are also going to use all these techniques from those chapters. So more interesting is the rotation about a fixed axis. So you can see here there is an axis. All the points in this axis, they are not moving, they are not rotating or translating. And the points that are not on the axis, they are moving in circular path. So they all have circular paths. That's the defining key of translation. And when you combine the translation and the rotation, you get the general plane motion. So here's an example of a piece that has many this piece of machinery has many pieces, and each one has different types of motion. So if you look at this one here, so that one is just doing a pure rotation about this axis here, an axis perpendicular to the page and at that point there. If you look at this one here, right, this disc, that disc is also doing a pure rotation. Now, this this piece here, this link, is just doing a curvilinear translation, right? The orientation, this line here is always horizontal, so it never changes orientation. Same for this piston here, but this is doing a rectilinear translation. Now, this link here, this is the most interesting one in this machinery, and that is doing a general plane motion where it has a translation and a rotation in it. So let's introduce a little bit of notation. Here we have a rigid body. This blue potato is a rigid body. And so we want to describe, to define a notation to describe points in this body. So we have a point B, a generic point B, and that point has a vector position RB. So what we want to do is we want to be able to write this in a clear manner. So RB, we are going to say that the vector RB, right, is equal to the vector RA. What is RA? RA is a vector that goes from the origin to point A plus the vector from A to B. And so to write that, we're going to write vector A relative to B. And that's a notation that we have to use, that we're going to use. So you have a fixed coordinate system, a coordinate system attached to the body. This is the translating coordinate system. You want to describe points in the body, right, like RB, and then you use that by using the attached coordinate system, right? So and you look at the position of the origin of that moving coordinate system and then points relative to that coordinate system. So that is the notation that we're going to use. And now we can take derivatives, right? So if we take derivative of RB with respect to time is equal to derivative of RA with respect to time plus derivative of RB relative to A with respect to time. What is this? This is V, the velocity of point B, right, as seen from the fixed coordinate system. So, and that is equal to the velocity of A as seen from the coordinate system, the fixed coordinate system. And then this one here is the velocity of B relative to A. And we have seen this when we study relative motion. This is a similar notation. Now, if there is a pure translation, this guy is 0, right? If there is a pure translation, this guy is 0, and then you get that BV is equal to VA, and also AV is equal to AA. So these are the key features of translation. So this and this here, those two equations. So when we talk about pure rotation, right? So we need to remember how we define rotation. So for that, we have to define what is called the angular position theta. And we also have to define the angular displacement, right? So when a point moves an angle theta, like this one here, right? So there is an angular displacement. Remember that we are going to use radians, and one revolution is just 2 pi radians, right? So the angular velocity is just displacement divided by time, so d theta dt, and the angular acceleration is the second derivative, right, of the displacement divided by time, or the change in angular velocity with respect to time. So these are equations that we're going to use. You're familiar with this from Physics 1. So we're going to use those equations. And a key simplification happens when we have constant angular acceleration. If you remember your kinematics from Physics 1, this is V is equal to V0 plus AT. It's a similar equation for rectilinear motion. And then you're going to have that X is equal to X0 plus V0t plus 1/2 AT squared. And finally, you're going to have that V squared is equal to V0 squared plus 2 times A and delta X. So these are the equivalent equations in rectilinear motion, and these are the equations that we are going to use when we have constant angular acceleration, and many problems will have that feature. So let's look at a little bit on how to write the velocity of vectors using angular acceleration. So if you have a vector, if you have a point rotating about an origin, right? So remember that we can write that the velocity of this point is omega r, right? If this guy has an angular acceleration omega. That is Physics 1. So what we want to do is write this using vector notation. So this is a part of a more complicated rigid body that is moving in this way here. And then we want to write this vector v. So if we look at this, this is your angular acceleration. It's a vector that goes along the axis, right? So that's omega. So that's omega. And the vector position of this point P, if this is your origin here, right? So this is your origin where you're setting your coordinate system. The vector position is going to be R is equal to, well, this vector here that we're going to call R parallel, right? So that's a vector along the axis of rotation plus a vector here that I'm going to call RP, right? So this is RP, this vector here, and this is R parallel. So now what happens if I take the cross product omega cross R, right? What happens if I do this? Omega cross R, right? So if I do omega cross R, omega is a vector that is parallel to this vector, so those two are going to be 0, and this is just omega cross RP, and these are all vectors. So what we are seeing is that the velocity can be written as omega cross RP, or which is equal to omega cross R. So, and this is the equation that we are going to use to describe the velocity of points in a body that is doing pure rotation, omega cross R. So now let's take derivatives of that vector there. Let's take derivatives and see what happens. So remember, the point P is rotating about an axis, so it has a tangential and a normal acceleration. So then we can calculate that. So the acceleration, right, is always dv dt, right? And so from the previous equation, what is that? This is d dt of omega cross r, right? And now I can apply the product rule here, and this is d omega dt cross r plus omega cross dr dt, right? So, and dr dt, so let's just look at this slowly and see what happens here. So this is what? This is the angular acceleration. So this is alpha cross r, right? And then this is omega cross dr dt, but dr dt is omega cross rp from our previous omega cross r from our previous equation in the previous slide. So this is what I get here, and then I can simplify this as alpha cross r minus omega squared r. So that's how you write the acceleration, and you can then equate this to, this is your tangential acceleration, and this is your normal acceleration. So this is how we're going to write the normal and tangential accelerations in pure rotation. So we are going to now look at some procedure to talk about rotation of fixed axis problems. So you need to have a sign convention where we're going to use the right-hand rule. And then we are going to look at relationships between the variables alpha, omega, theta, and t. And so, and if you have an equation between any two of these, then the other two can be found by using